Alright, today we're going to be looking at the TP-Link Archer C7 router. The objectives for today are to try and find a UART shell in the device, to pull the firmware from the device, and based on what we can find in the firmware, see if we can get root access on that shell. So the first thing we're going to be looking at is points of interest. And the first place I start with this is usually FCC filings. Any device that is going to be emitting a signal has to register with the FCC, and part of that application process involves submitting internal and external photos. So if we look on this device, we can see on the back label they actually provide the FCC ID, and it's usually going to be somewhere on the device or in the manual. The FCC website is a little hard to navigate, but there's a few others like fccid.io, where you just type that in followed by the FCC ID, and that will take you right to the exhibits for that device. So here we can see, if we scroll down, you can find the internal photos, test reports, all of the interesting documents we want to look at. So I went ahead and pulled the image that they submitted for their internal photo. And this is why it's good to look at this even if we have the hardware, is you can compare that to this image that I took, and you can kind of see a few things that are different. Looking at these unpopulated headers, we see that in testing they actually populated it. And this is a good indication that the signals on this header are something that are used in development. So we can keep looking at this and try and find some points of interest on the board. The big ones that jump out to me are, obviously we have a few large ICs here with clock sources nearby, and we can kind of run those down, and we're trying to figure out which one is the main CPU for this board. In this case, I actually looked into part numbers, and this Atheros is just an Ethernet switch. And then down here we have this Qualcomm part with, you can see a clock source here and some external RAM here, which is a very good indication that this is the main CPU we're going to be interested in. And then we can also see a number of these 8-pin SOIC packages. And again, you can just kind of run part numbers down, or you can kind of look for context clues around it. For instance, these are all near large capacitors and inductors, kind of indicates that they're part of the power supply system for this, where this one over here is, near the processor we're looking at. So to me, that looks like a good candidate for a SPI flash chip. And if you scroll down, I just kind of highlighted some of these. I pulled part numbers, so we can look those up. And this is in fact a SPI flash. Pulled the part numbers for this Qualcomm processor. And then we have these two interesting headers over here. And I labeled this one as a possible programming and debug header, just because it's not a standard pinout that I would expect to see, but it's a lot of signals, which makes me think that they're doing some sort of program and debug with it. This one down here is just 4 pins, and that's a really good indication of a UART interface, because you need your ground voltage if you want to power it, and then TX and RX. In some cases you'll see this as just 3 pins if you don't need to power from this interface. So the first thing we're going to do is start looking at that UART interface, or that possible UART interface. And we're going to start looking at the pinout of that. So here I took an image and just labeled it. In schematics, you'll usually see, or on the silk screen, you'll see this white box around a pin, and sometimes they'll do a square pin. In this case, they did both to indicate pin 1, just to line up with the schematic. And I'm going to pull up the microscope view here. So we need to find ground, VCC, TX, and RX. So we can start looking at what we expect to see on those signals. And ground is going to have continuity with a known ground point on the board. Good place to look for this is something like any RF cans, any shielded USB receptacles, which we can see a few on our board. So we can just check continuity between the pins and those and see if we can find which one of these is ground. And then we're going to look at for one that is high relative to ground. It'll be a 3.3 volt signal that is kind of a steady high signal. The next one we're going to expect to see is a TX. And while the board is booting and this is transmitting, we should see this fluctuate somewhere between 2.4 and 3.3 volts. And the reason for that, we can kind of look at this UART trace here. UART is an active low. So at idle, the pin is going to be high at 3.3. And then as it clocks out data, it's pulling it near ground. So it's going to kind of bias on a multimeter which can't keep up with that speed. You're not going to actually see it go from high to low. It's going to average over time, and you're going to see it kind of bias towards high just because the idle is high, and that's where it's going to spend most of its time. And then the RX pin, we're not going to see any voltage on it. It's going to be floating, so near 0 volts, but it won't have continuity to ground because it's not connected to anything. It's expecting someone to connect to it externally. So let's go ahead and take a look at that. All right, so I'm going to first look for ground. It's usually good to start with that one so you have something to reference your voltages from. So I'm going to put one probe on the USB receptacle and then just start looking at these other ones to see if I get a tone. And we can see there on pin 3, we have continuity ground. And another thing you can look for here is you can see that around pin 3, it has 4 different connections from that pad out to this ground port around it. And that's for thermal relief, and it's another good indicator that it's a ground signal, but it's always good to check with a multimeter. So now that I've identified ground, we can switch over and look at the voltage, and we can start using that ground as a reference. I'm just going to power on the device and referencing ground. We'll start with pin 1, and we see pin 1 is at 2.5, 2.4. It's kind of moving around. So to me, that's a pretty good candidate for TX. We can see it just moving around there. Now pin 2, just a very low floating voltage. It's not quite ground, doesn't look like it's connected to anything. So that is likely going to be our RX, which means pin 4 is probably voltage. And yeah, we've got like a pretty steady 3.28, 3.3. So that gives us our pin out for this UART connection, and now we can tie into it. So I'm just going to break off some pins that we could put in there. We don't need to solder them in. We should be able to just put them in and push it up against the side. Power it off while making this connection. And now over here we can open up PicoCom and power it on. And there we can see we are getting the boot log and we saw there momentarily we got a login screen, but it's just going to keep scrolling. We'll wait for this to finish. It's not root, so we need to figure out what the actual login and password is. So that's going to be our next step. What we're going to do to accomplish that is we're actually going to pull the firmware from the device. And if you'll remember, we found that chip that we believe, or we know it's the SPI flash because we looked at the part number. So now we're going to connect to that and try to pull the firmware from the flash chip. So this shows the pinout. These are the signals that we're interested in. The two X's, we actually don't care about those. We don't even need to connect to them. You can connect to these individually using logic probes, or in my case, I have a clip made specifically for this style of chip that just clips right onto it. So we're going to hook that up, and we're going to use the Linux Flash ROM utility and see if we can pull that firmware. So we're going to power off the device. That's down there. And you can see the lights come on where it is powering it through that chip because that pinout does include a voltage pin. So let's just go ahead and see if we can read that. So we're going to run Flash ROM. Your connection string might vary if you're not using a TiGuard, but it does support a lot of different hardware. You can check the Flash ROM manual for more information if you're using something else. So we'll run that, and we see that it cannot connect to it. And the reason for this is that when we are providing power and we're powering up that chip, we are also powering up the main processor. And the main processor is asserting these MOSI and clock signals, meaning we can't toggle that. We're in contention with this other chip. So there's a few ways around that. The most reliable way is to desolder the flash from the board and put it in a flash programmer and read it that way. I say reliable because this will always work, but it is less reliable in the sense that you can damage the part. You have to really clean the pins off in some cases, and it's quite a bit of work. Another way is if you can power the flash chip without powering the processor. That's another workaround. It's usually not that easy to do though, because if they are running at the same voltage, it's really hard to have one of them not powered on while the other is powered on, because they are going to share that connection. And then the last option, which I usually prefer, is to disable the target processor. And this really depends on the processor, but there are a number of ways to do this. Most processors will have a reset signal, and when you pull that reset signal low, it's going to hold the chip in reset, and it's going to hold all of the pins in a high impedance state, which effectively disconnects the internal logic of the chip from the physical pins, and this will release the pins we care about and let us take control. So in a lot of cases, you can just look up the data sheet for this, and that's a pretty easy way to go. Find the reset pin. Sometimes you'll find something else, like a test mode pin. In this case, though, it's Qualcomm. They do not publish data sheets unless you're going to buy a very large quantity of their chips. They're not going to give you a data sheet and tell you how it works. So we're going to have to do a little RE and see if we can find the reset signal on our own. So we can make a few assumptions about the reset signal, just based on some past experience. They are almost always active low. I've never seen an active high reset signal, and what that means is the pin should be high at an idle state, and then when you want to reset the processor, you would pull that low to ground. They are usually held high by a resistor, and the pull-up resistor is usually a medium-high value so that it can be easily driven low by a switch or an external programmer. 10K is the most common that I've seen. 4.7K is also somewhat common, and this is because that's the standard pull-up resistor for I2C signals. And if you're doing the manufacturing, sometimes it's cheaper to just have a lot of the same part on your design, or if you're using a small pick-and-place machine, the cartridges can only hold so many different parts, so you try and reuse where you can. Another assumption is that it's going to be connected to a programming and debug header. Some debuggers, you can set the reset strategy to get into debug mode where it needs to actually toggle that reset line. So in most cases, you're going to be breaking out your reset signal to your programmer. And it's also usually one of the earlier steps when you're designing a board to put in your reset signal. And this is a lot of speculation, but when you're adding a component to the schematic, it's kind of natural to set up your power and your reset and just anything mandatory first. And speaking to that, we're going to talk about some of the strategies with reference designators. And these are, if you look at the silk screen of a board, these are the ID numbers that go along with all of the components. So you'll see, R93, R94, things like that. These are the reference designators that are used to ID each of the components during the manufacturing process. And there's a few ways that you can organize these. The most common one that I see is to not organize them. Basically, they're going to get an ID number based on when they were put in the design. So the first resistor you add is going to be R1, and it's just going to keep going up from there. Another way to organize is by location. So they have scripts in a lot of the PCB layout tools. Once you get your layout complete, you can have it rename all of the reference designators based on their location on the board. So for instance, you might start in the top left with R1 and then work your way down into the right. And that just makes it kind of easier to find a component if you know the designator. And then the last one is going to be by subsystem. And this will usually rename smaller components to match the larger component they support. So if you have a processor that's U1, you might have all of the capacitors supporting that start with C100 and then the number that they were put in. And these two, by location and subsystem, they're very common for small batch manufactured boards, because if you have to assemble one by hand, it makes it a lot easier to find where components need to go on the board. Looking at our board, it doesn't look like they did either of these strategies, so it looks like there's no organization, and we can assume that something with a low reference designator was put in the design early on. And that ties back into our assumption that the reset circuit is probably one of the earlier steps in the design process. And this is all, like I said, speculation based on my experience, so I kind of wanted to test this. So I went back and looked at some open source projects to see how those assumptions hold up. And we can see here, I looked at 5 boards. 3 of them have pretty low reference designators for their reset pull-up resistor. This one is 1002, but that's because they're using that subsystem strategy for naming their components, and you can see that it's supporting U1001. And the value for all of them fell pretty close to 10K. They were all 10K except for the ESP32 development board. And just a side note, in the 2 that didn't have low reference designators, R1 and R2 on both of those were used for the USB to microcontroller signals. So it seems like they connected the main interface for that, which was a USB interface, and their power circuits before setting up the reset signal. So now we can start looking for our reset signal, and we can go back to our assumption that it's probably going to tie in somewhere with the debug and programming header that we found. We don't know what any of these signals are. It does not follow a standard pinout for a programmer that I know of, but it's a good place to start looking. Alright, so we can start looking at these signals on the programming header and see if we can find any that are pulled high. So we're just going to pull ground from the UART connection since we already know what that is. Power board on. So nothing on 1, 3, 5. And we're just looking for something that's going to be pulled up to 3.3. Now that's an interesting one at around 2.6, and it doesn't look like it's fluctuating too much. So I don't think that's our UARTX broken out to a different header, but that is something that we can definitely come back and look at when we try to pin out the actual programming interface. So we don't see anything on here that is 3.3. But something interesting that we do see is this R10 resistor right here, which is not populated. And sometimes unpopulated components can kind of point to an interesting signals. So it's something that maybe they needed that circuit in development or testing, but they don't care if it's there in production, which is definitely something that you would find with like a reset or a programming interface. So let's go ahead and look at the other side of R10. And we can see that that is 3.3 volts. So we can check one of our other assumptions. We think it's going to be pulled high with a 10K resistor. So we can hit on there, and then we can measure the ohms between that and our voltage that we know in this interface. And we can see 9.96K. So that's a 10K pull up on this signal. There's likely a 0 ohm resistor here to connect it to this header. So to me, that is a pretty good candidate for a reset signal. So let's go ahead and test that out. We can get one of our pins. So we will connect that, which is ground, and we're going to use one of these PC Byte probes. Might be kind of hard to see. But we're just going to place it on that pad for the resistor. And then turn the device on. And already we can see the LEDs are acting a little differently. Before we would see all of them light up and then have some sort of status pattern to them. And now we just see that there's one lit up and the rest have gone off. So that looks like a good sign to me. Let's go ahead and put our SPI flash clip on. switch this so that we use the target voltage, so we're not powering it. Alright, and then we go back to flash ROM. Alright, so now we can see if we can read from this chip. And what's interesting here is that it's detecting it, it can read from it, and it looks like it's not able to detect just on the ID the exact variant of the chip. What's interesting is I pulled firmware on an identical router when I was writing this up, and I did not get this, so I believe that they're actually using a different flash chip on this board than what I had used before. And this is actually kind of common, and these chips are pretty interchangeable. They all follow the same protocol and standard. But you know, with supply chain issues, they might have just had to switch to a different manufacturer when they made this batch. So we can just specify the chip we want, and I believe it's a 64K page. All right, and now we are reading in the flash. And it's a good idea to do this a few times. Yep, and all of the checksums match, so it looks like we have the firmware. So we can go ahead and get rid of these extra ones. And now we're going to take a look at it with binwalk. So it's showing certificate, U-boot, some other information, firmware, and then this SquashFS file system, which is what we're going to be looking at now. And what we're looking for here are the credentials so that we can log in through that UART shell. So with Linux, it stores that in the shadow file. So if we go into our extracted data, into that SquashFS root under Etsy, we can look at the shadow file. And this is going to show us that we have a user named root, and this section is the hash of the password. So this is going to be split up into 3 sections separated by $signs. The first one shows us the type of hash used. The second section is the salt for the hash, and then this last section is the actual hash of the password. So we can create a text file with that. So let's copy that. And we're going to store it in hash.txt. And now that we've created that file, we can use Hashcat to try to reverse that hash. And we'll just go briefly over these settings. -A3 says that we're trying to do a brute force attack. The M flag tells it what type of hash it is. In this case, 500 matches up with the $1. And you can see that by just searching the Hashcat options for $1 or $whatever you find in the shadow file, and it will give you the Linux hash equivalent. Give it our hash file that we just created, and then this is a pattern for the brute force attempt, and it's going to look for any 4 lowercase letters followed by admin. Actually, I have 5 there. And I just know this pattern is used a lot in these devices. It's usually some lowercase string followed by admin, and I just tried a few different. So I tried it with 3 letters and then 4, and I would have kept going and looking around different counts. But in this case, it was 4. Oh, and this is the ZSH just not liking something there. Oh, we can. So it's going to start up Hashcat, run through, and here we can see that it cracked it, and the password it came up with is Soho admin. So we can go back now, and we're going to connect to that shell again and see if we can try with the credentials root Soho admin. So we can open our terminal back up, power on the device, and we'll wait for that to finish booting. We'll try our credentials that we found. And we can see now we have root access on BusyBox.